Hi, my name is Dr. Mehdi Khan, and today I'm going to give presentation for the job in a School of Engineering in Pakistan. Um, and topic which I choose today is a gallium nitride and large signal model come high power amplifier. This I'm going to talk about my PhD work, kind of a PhD work, one type of PhD work. It's large signal model for transistor, and then we use a high power amplifier to test the transistor models that it is accurate or not. This work is being done in micro nano electronic system center, which is we call MESE, and 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 the university name is University of Science and Technology, which is situated in Hefei, China. And I work with Professor Ling Fuzhong, a Chinese professor, and he's quite famous for the large signal models. So we work together on this project. So first of all is the outline. I'm going to talk about the attributes of the gallium nitride HEMT, why we need gallium nitride HEMT, why it is very good. And then I'm going to talk about the model types, what type of models in the market, what type of models currently in the commercial. Then I'm going to talk about the large signal model, a normal large signal model and normally people use, and what things inside the model, what you can see. Then I'm going to talk about the transistor modeling sequence. How can you make a transistor model? How can you make a large signal model? How can you make a small signal model? And what are the differences between them? Then I'm going to talk about the trapping effect. What is the trapping effect? Because transistor model have so many effects: the thermal effect, dispersion effect, capacitance effect, inductance effect. So this is one effect which I'm going to talk about, and it's very important nowadays. And afterwards, I'm going to talk about the model verification. How can we verify the transistor model? Normally we use power amplifier for the gallium nitride. So if it is indium phosphate, then it's known as amplified, because gallium nitride is famous for the high power. So that's why. And in last, I'm going to talk about the new drain equation, which is being derived because of the trapping effect. And whenever we put new effect, we try to change a little bit, sometimes drain equation, to make it more accurate. And the last is the conclusion. Here we go. So why it is being motivated people like work for the gallium nitride HEMT? Why? The very important and the first thing is the band gap. It has the very high band gap as compared to silicon, which is quite famous for RFIC design, which is quite famous for the Bluetooth and everything, like smart cards and everything. And what happens if we have a wide band gap? It means we can achieve a very wide frequency range using one transistor, as compared to silicon, which is a narrow band gap. You need multiple devices, multiple power amplifier for specific frequency, but gallium nitride HEMT can do it with using one transistor. This is the very important thing of this transistor. Second thing which I'm going to talk about is saturation electron velocity. It has a very high electron velocity. That means very good for switching. It can be working. It can work as a switch very fast as compared to silicon and gallium arsenic and other things. And it has a high breakdown voltage as compared to silicon, which is 0.3, and it has 3.3. It is like 5 to 7 times high breakdown voltage. That means if you give a very high voltage, it will take time to break as compared to silicon, which is 0.3 voltage per centimeter. And it has a dielectric constant, which is 9 of a transistor. And now I'm going to talk about the types of model. What type of model commercially available in the market? Here we go. So commercially compact FET models are these. Like one is the Curtius 3 number, and it has a number of parameter 59. I will tell you what parameter means in next slides. It has number of parameters 59, and it doesn't have electrothermal effect. It doesn't have trapping effect, and it was used for gallium arsenic in 1960s for FET. So, but it was good at that time. But nowadays people don't use this thing. They may use, but it's not famous because it's no more accurate. Afterwards, it came CFET, which is a bit better than Curtius because it has 53 parameters, less parameter. It also has thermal effect, and it can work with the gallium nitrate like HEMT, but it doesn't have trapping effect. The third one, which is famous, which is still using in the market, is HEMT. It has number of parameters 71, doesn't have electrothermal effect, doesn't have trapping effect, but still it is very good because it's more accurate than Curtius and CFET because of it has so many parameters which it covers many things. Then a new one just came 5-7 years ago, MCAD, by a French company. It has number of parameters 65. It has electrothermal, it has thermal trapping effect. It has both effects, and it is very good as for the gallium nitrate HEMT. Now I'm going to talk about the Angelov model, Clausen model, which have number of parameters 80. It has electrothermal effect, but it does not have trapping effect. But it is more accurate than others like MCAT, even though it has trapping effect. It is very good. It's used for gallium nitrate HEMT, mass spec, even gallium arsenic. And the last one is going to talk about enhanced Angelov model, which is we made it using the Angelov model and we put a trapping effect which it does not have, and it make it more accurate. So we put 4 more parameters, and it's best for the gallium nitrate HEMT, and it's more accurate compared to old Angelov model. So type of models. So there are 3 type of models in the market like people normally make. One is a physical model. Physical means physics. We use totally equations, and we see it like the oxide thickness, and we use equation, doping concentration, carrier, mobility, many things we see using mathematical equation. We try to make a model. It's totally mathematics based, and through equations we make this model. And the second one is the empirical model, which is our model. It is more like curve fitting. We make a curve. It is an IV curve. We use some semiconductor parameter analyzer. We see the IV. We see this is its curve. This is VD curve. This is capacitance curve, and we try to fit using equations. If we see this is the curve, is like electron 1 over E, so we use that equation and fit that curve. It's quite famous, and it is like we call it fit the, and use some simulation and fit the curve by using some matrix models. And the third one is the tabular model. Tabular is more like kind of like a black box. The input is like some numbers. You drive some numbers, and you see these numbers is very fit for this IV curve, and it is more like in computers we can say like machine learning. It is all auto algorithm kind of this thing, and automatically it drives it and it fit it. So it is more like tabular. We call it tabular. And now I'm going to talk about the large signal model, which is quite for like normal large signal model, which for every transistor normally people use it. So here we go. This is the large signal model. As before I was telling about the parameters, number of parameters 59, number of parameters 53, 71. So these parameter means, if you can see there, you can see capacitor, inductance, so many capacitor, resistor, and diodes, whatever. So these means the parameters. So a large signal model, if you can see from here, it has a gate. From the left side you can see, and the right side is the drain, downside is the source. So gate side has some inductor and capacitance, which means it is the leg of the transistor. A metal leg means it has some inductors and capacitance, same as for the drain side and the source side. And the box, if you see, it is the inside of the transistor. The outside is the passive components, passive side, and the inside is the active side of the transistor. It has GM, that means the gain of the transistor. So this is a normal large signal model of a transistor. So now I'm going to talk about the enhanced large signal model, which is our model. It has all effects, which is Angelov have, and we put some 8 parameters that effect. If you can see on the left hand side, on the drain side, you have 2 resistance, diode, and a capacitance. and on the right hand side 2 resistors, diode and a capacitance. To make this is a trapping effect, we put more parameter inside so that the transistor model can become a more accurate as compared to before. So that's why we put this effect inside. So this is the chip side, and that also outside we call off chip side. So transistor model sequence, how transistor model sequence normally works. So here we go. This is a transistor modeling sequence. How we can make a transistor model. First of all, we go for the small signal. Small signal means linear. When we have IV, a linear side, we call this is a small signal. Large signal means it is a non-linear effect. So small signal, you can see we can if we have a small signal IV and other parameters, we can drive. We can take the values. We take out the values of resistance, like you can see the gate resistance, gate inductance, capacitance, source inductance, capacitance, drain capacitance, inductor, and everything. And also we can get the GM and GDs and other capacitances in using small signal analysis. After we go for small signal, we go for the large signal analysis, large signal model. Then we can get the nonlinear effect, that means nonlinear capacitances, and we can go for the IV to know the drain voltage and the gate voltage. This is the large signal model. Afterwards we can have other effects, which is we call thermal effect and trapping effect, and these all effects are we can derive from the large signal model, that means non-linear effect, not from the small signal analysis. So this is the normal sequence of a transistor modeling. You can see first is small signal, non-linear, IV model, and thermal, and then in the last is the trapping effect. So now I'm going to talk about what is the trapping effect. Trapping effect is like kind of a if you can see the transistor, it has some kind of aluminum gallium nitrate and gallium nitrate layers, and in between those layers it has some kind of it touches it makes some effect, which is we call when we give a short pulse, very short pulse in nanoseconds, you can see a trapping effect. That means it didn't switch on, it takes time to switch on, as you can see from the left hand side graph, IDS, it takes time to on. This is we call trapping effect. And we can say it has a gallium nitrate buffer layer. In gallium buffer layer, between that we can see that effect, and we can have it when we give a gate voltage, and we can see the gate trapping effect, and then we can see the drain trapping effect by giving a drain voltage as pulse. We normally don't give a continuous voltage, we give a very short pulse, nanoseconds, to see the trapping effect, and then we get the value of a trap effect by these equations, which you can see on the downside. These equations can give you the values of the trapping effect. So what is it? If you can see from here, a normal IV red color is without trapping effect. When we put a trapping effect, you can see a drain lag. That means drain get back, and there is a gate lag. That means gate go down as compared to normal IV. This is a normal IV of a transistor, and it also have a trapping effect, which is a blue color, and the red color is a normal IV effect. And then when we have a normal effect, we put a trapping effect, it becomes a trapping effect transistor, and you can see it shifted left. That means it will shift the drain current as well, drain equations as well. So that's why we change the drain equation as well, because it changes the everything. It changes the IV. So now I'm going to talk about the model verification. How we do the model verification? Normally we design from a power amplifier. If you can see from here, this is IV of a power amplifier, and on the right hand side you can see my name on the transistor, Mahdi gallium nitrate. This is our model which we make, and you can see so many parameters inside. These all parameters we can derive from the, like I said before, the sequence way, and then we put this value inside, and then we verify the transistor by putting the value, and then we measure the transistor, and then we check with the measure and with the simulation how accurate it is. And downside you can see the load pull of a transistor. This is because power amplifier, then we talk about also load pull. so that we can get the power and the PAE, power added efficiency of a transistor. So from here you can see a normal on the top one, it has IV 46%, and this is output power, PAE input power. If you see on the downside, a transistor with no trapping effect, it has this curve of a PAE, like a kind of sharp top one, and you can see the green one is a trapping and temperature effect. It goes down because it's become more accurate, and these values also show in the measurement that this trapping effect is more accurate. And the last one, the drain equation. This is the drain equation, normal drain equation of a transistor. Then we put a new equation, you can see with the temp tau, with the temperature, and 1 plus VGSNS, 1 plus VDSN, as this is the trapping equation, and which we put inside and make it more accurate transistor. And in last conclusion, we propose a new large signal model, verify the model with power amplifier design, and we design drain, and we also modify the drain equations. And this is the reference. Thank you very much.